All right. Hello and welcome to lesson 10.6. Got some new technology I'm going to try to use. It's not gone well so far. So I'm going to try this again and see if it works. We're going to be looking at the ratio test for convergence, which is one of the last major tests for convergence that we'll study. And it is extremely useful for a couple of reasons. And what it says is this: if we have some series, a sub n, with positive or negative terms, and we know the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, so some term divided by the term before it, so the ratio of those two is some limit, then the series will converge if the limit is less than 1. The series will diverge if the limit is greater than 1, and the test will be inconclusive if L, the limit, is 1. We call this the ratio test because we're taking the limit of the ratio of some term to the term before it. This test is one of the most useful for analyzing different facets of series, as we shall see. It also gives us a way to look at the convergence of series that would otherwise be kind of challenging to analyze, like when we have series with factorials and things like that. All right. So we're going to take a look at this series down here. We're going to determine whether or not this series diverges, okay? I want to really try this pin out. I'm really hoping I can get this swing at this, so please be patient with me here. All right, so really what do we want to figure out? We want to figure out this. We want to figure out if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, lost my dividing bar, over a sub n, what that limit is, okay? Now this is going to look really funky at first, but what we're actually going to have to find then is the limit of this thing with n plus 1 plugged in divided by this thing with n plugged in, which is what we're looking at here. Let's deal with the more complicated part of this. Let's plug in n plus 1 for everything. So what do we really want? We really want this. We want the limit as n approaches infinity of the absolute value of negative 10 to the n plus 1. Notice I took this over here and I plugged in n plus 1 over, over all of this stuff with n plus 1 plugged in, which starts to look really funny because we have 4 to the 2n plus 1. So what is that going to look like? It's going to look like 4 to the 2n plus 1 plus 1, all in the exponent up there, times the quantity, all right, n plus 1 plus 1, all right, all down there. So that looks kind of crazy right now, but here's the deal, right? We want to take that and we want to make sure, so this is the absolute value bar, it goes all the way down. We want to divide this by this whole thing right here, all right? Which would be, when I come over, I'm basically just going to copy and paste this stuff down as is. Negative 10 to the n over 4 to the 2n plus 1 times n plus 1. There we go. We're going to divide by all of that and take the absolute value. Okay? Notice we took this series, plugged in n plus 1 for all the n's, and we're going to divide it by this over here. Looks really messy, so usually what you'll see people kind of immediately come down and do is this. We're dividing by some big thing here. So we're just going to say, hey, what we're really doing is we're multiplying by the reciprocal. We're going to clean up a bunch of stuff up here to make this a little easier, okay? So what we're going to do then is say this. What we're really interested in then is the limit as n approaches infinity of the absolute value, right? The absolute value of, and we're going to clean up that whole upper part of this fraction. Negative 10 to the n plus 1 can't really change, right? Over, when we clean up this whole denominator down here, I'd end up with 4 to the 2n, distribute the 2, plus 3. So 4 to the 2n plus 3. 4, 4 to the 2n plus 3. Let me try that again. 4 to the 2n plus 3. All right. By cleaning up that numerator times, let's see, that'd be n plus 2 in the denominator down there. N plus 2. All right. And I'm going to flip this whole denominator down here to multiply by it, okay? So drawing that out, I want to multiply by that denominator reciprocated. So this will make up top here 4 to the 2n plus 1, 4 to the 2n plus 1 times n plus 1, all over negative 10 to the n, which will go down there. Negative 10 to the n. I want to take the absolute value of all of that. So I've cleaned up this whole big mess up here and said, hey, it's actually equal to this. Now we notice a few things, right? I notice that I have negative 10 to the n plus 1, negative 10 to the n. Well, let's see. We can use some properties of exponents to come up with how we can simplify this. Negative 10 to the n plus 1, negative 10 to the n. The negative 10 to the n's will cancel out and leave us with negative 10 to the n plus 1, right? That leaves us with negative 10 to the 1, because negative 10 to the n, negative 10 to the n, those will cancel out, right? We'll get with negative 10 to the 1. So that'll clean up a little bit there. My n plus 1 and my n plus 2 aren't going to cancel anything out, but this looks very similar too. I'd have 4 to the 2n plus 1, 4 to the 2n plus 3. Well, the 4 to the 2n's will stay, and I have a plus 3, a plus 1, so I'd have a 4 squared left down here, because the difference between this 1 plus 1 and plus 3 is a 2 down here. So let me rewrite this then as the limit as n approaches infinity of, I'm going to cancel everything out now and clean up this absolute value. My negative 10 to the n, negative 10 to the n will go, a lot of that will cancel out. I'll be left with negative 10 just kind of by itself. Negative 10 to the first power. My n plus 1 is going to stay up here. My n plus 1 is going to stay up here. All right, he doesn't have anything to cancel out with. 4 to the 2n plus 1 and 4 to 2n plus 3. Most of that will cancel out except for the 4 to the 2. So that'll stay in the denominator down here, right? So I can go ahead and call this 4 squared if I wanted to. All right. And then my n plus 2 is going to stay down there also. And this is the thing about the ratio test, which is kind of nice. If you've done everything right, a lot of stuff will cancel out. All right. Everything but negative 10 to the 1 canceled out. My n plus 1 stayed. 4 to 2n plus 3, 4 to the 2n plus 1 left us with a 4 squared because the 2n's canceled out, and the 1 and the 3 gave us a 2 left in the bottom, and the n plus 2. Go ahead and close off this absolute value bar. And let's see what we got here. Well, as n goes to infinity, this n is going to win up top. This n is going to win down here. So really, these things go off in the same direction. We can clean, or at the same pace, we can go ahead and clean this up if we want to and distribute out what we're looking at here. What we really have then is the limit as n approaches infinity of the absolute value of negative 10n minus 10 over that 4 squared is a 16. I would have 16n plus 16 times 2 will give us 32, right? My plus got a little funny looking there. All right. So cleaning this up then, we end up with something that looks more like this, right? 16, negative 10. All right, we take the limit of this and take the absolute value. Well, our negative 10 and our 32 don't matter. We end up with negative 10n over 16n as n goes to infinity. Those will cancel out. And we end up with the absolute value of, this is going to be equal to the absolute value of negative 10 over 16. Which is going to be equal to 10 sixteenths, which is equal to 5/8. All right. And what did we just figure out? 5/8. Well, 5/8, there's my limit. 5/8 I know is less than 1. Whoa. 5/8 I know is less than 1. So I know then, based off of my ratio test, my ratio is less than 1. so that then I therefore know that this series definitely converges. All right. Thanks for also being patient with my new pen system here. I'm working on it. All right. So let's take a look at another one. I'm going to get rid of that. As another example, a slightly easier one. I actually like to start off with a more complex one there to kind of get the whole picture. Here's a good one. Let's take a look at this one and give it a shot. Again, we're going to really be looking for the same thing. What am I looking for? I'm looking for the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, right? Okay. What does that look like in this case? All right. This means I'm looking for the limit as n approaches infinity of the absolute value of, okay, I need a sub n plus 1. So what does that mean? I'm going to need n plus 1 factorial over 5 to the n plus 1. 5 to the n plus 1, right? Okay. That whole thing divided by n factorial over 5 to the n. Absolute value of all of that. All right. And what have we said about this? Well, we said, okay, we really just have to flip and multiply by the reciprocal. So what am I looking at here? I'm really looking for the limit as n approaches infinity of the absolute value of n plus 1 factorial over 5 to the n plus 1 times the reciprocal of this, which I know is 5 to the n over n factorial, close the absolute value. Okay, so what do I know here? Interesting. So this over here, that should be a 1. 5 to the n plus 1. So the 5 to the n's will all cancel out, leaving us with, remember, if you use your exponent rules, 5 to the n plus 1 is really 5 to the n times 5 to the 1. So the 5 to the n's will cancel out, leaving us with a 5 to the 1 down here. N plus 1 factorial. Remember, factorial is telling us, take this thing, multiply n plus 1 times n minus 1 times n minus 2, multiplying itself down. Like 5 factorial is 5 times 4 times 3 times 2 times 1. N plus 1 would be n plus 1 factorial is n plus 1 times n minus 1. So what did we realize? Oh, well, n plus 1 factorial is really n plus 1 times n factorial. That's what I see down there. So I'm going to get some things canceling out. All right. So this is going to be equal to the limit as n approaches infinity of n plus 1 over 5. Again, how did I get that? Oh, so it's the absolute value there. How did I get that? N plus 1 factorial is n plus 1 times n minus 1. So if I take n plus 1 factorial, I could break it out over here if you want to think of it this way. N plus 1 factorial is really equal to n plus 1 times n factorial. That's what this is. And so I said, hey, I have an n factorial down here, so I'm going to cancel out n factorial with all of this, but it would leave me with the n plus 1. Okay? That's just an extra little help for how I did that cancellation. And the 5 to the n plus 1 leaves me with a 5 left over in the bottom. What does this mean as n approaches infinity? Wait, as n approaches infinity, that's definitely going to make the numerator grow. So what does this come out to be? This then heads to infinity, which I know is greater than 1. So what do I know about this series? It diverges. I should have said this for the last one. By the ratio test. Okay? Should have said the last one, converges by the ratio test. All right. Hopefully seeing those two examples, you can kind of get a little sense of what we're doing here. What I'd like you to do now is take a chance to practice the next two problems that you see there. Give it a shot and then come back to check your answers, okay? All right. let's take a look. For some of these, I want to sort of shortcut it a little bit. Instead of writing the big fraction, I'm just going to go ahead and do the multiplying by the reciprocal part. That way I don't have to, write out every time because it's what we're going to do every single time, okay? So let's see, we have n cubed over 2n minus 1 factorial. When we see those factorials, that's usually a big clue that the ratio test is going to be really useful for us. So I'm going to take the limit as n approaches infinity of the absolute value of, I hadn't switched over to my pen. Let's try that again. All right, let's do this. The limit as n approaches infinity of the absolute value of, let's see, we want to then do n plus 1 cubed over, this is going to look a little funky. We have 2 times n minus 1. So what is that going to look like for me? I'm going to have 2 times n plus 1 minus 1 down there. Okay? And then factorial. I'm going to extend that bar there. So here we go. This is n plus 1 plugged in for everything. We'll clean that up in a second. Times, again, is times the reciprocal of this that we're looking at here. Basically, we just copy it over, but we reciprocate it. 2n minus 1 factorial over n cubed, close the absolute value. So this is what we need to clean up now. I mean, we got to clean up my handwriting, but we can't really help that. All right, so what do we do with this? Let's go ahead and simplify what's on the inside, and hopefully we'll see some things cancel out, okay? So come over here. I'm going to do the limit as n approaches infinity of the absolute value of n plus 1 cubed. We got a little too close to our previous work there. Let's try it down here. The limit as n approaches infinity of the absolute value of n plus 1 cubed over. All right, 2 times n, 2 times 1 minus 1. So that's going to be 2n plus 1. So that's going to be my new denominator down here. 2n, let me back that up for a second. 2n plus 1 factorial. That's what I get down there, okay? Times, and I basically haven't changed anything from my other part of this. 2n minus 1 kind of just stays the same. 2n minus 1 factorial over n cubed, close the absolute value. Okay. So this has got us thinking a little bit. Okay, this is 2n plus 1. So some things will cancel out here. Let's see, 2n plus 1 factorial is 2n plus 1 times 2n times 2n minus 1. Now we get to being equal to that one at that point. Okay, so 2n plus 1 times 2n minus 1. That'll all cancel out there. So what is left over in this guy that's not here? 2n plus 1 times 2n is what's left over. All right. So we can simplify some of this stuff and simply say that this is going to be equal to the limit as n approaches infinity of the absolute value of n plus 1 cubed over 2n plus 1 times 2n. We also said that was left over down there from the factorials. Because then after we do 2n plus 1 times 2n, we get to the 2n minus 1 and keep multiplying down, and that'll cancel out there with the rest of those. And then what else do I have down in this denominator over here? I would have also in the denominator over here my n cubed, which is still hanging out. And then close my absolute value bars. All right, getting interesting here. So what happens? Well, as we see, we have n 2n times n cubed. That's going to give us something to the 5. That's going to give something, into the 5, like 4 into the 5th power. This is going to give us an n cubed out of this. So the denominator is going to win. So I know that this limit over here goes to 0, which I know is less than 1. So what does it mean? It means our series converges by the ratio test. Okay. Cool, let's take a look at the next one. Our next series looked like this. We'll go through the same thing. I'll kind of shortcut some of it just so we don't have to see all of the parts of this. All right, let's take a look. This is going to be the limit as n approaches infinity of the absolute value of, let's see, we need 3 to the n plus 1, right, over, it's going to be a little strange, negative 2 to the n plus 1 plus 1. So I'm going to go ahead and simplify that kind of in my head. This is going to be negative 2 to the n plus 1 plus 1. Oop, meant to write n plus 2 to go ahead and simplify that. Right, to the n plus 2. Draw that out over there. Times, let's see, n plus 1 there, right? Okay, there we go. So I've added n plus 1 to everything. And it's going to multiply by the reciprocal of this, because we would divide by it. So this is times. The reciprocal of that would be simply just copy it over, right? This is going to be negative 2 to the n plus 1 times n over 3 to the n, and then close the absolute value bar. All right, that absolute value bar got kind of far away. Okay, there we go. We might start seeing some things that might cancel out. I see 3 to the n, 3 to the n plus 1, so that'll leave a 3 to the 1 up over here. My n and my n plus 1, nothing can really cancel out there. I see negative 2 to the n plus 1 and negative 2 to the n plus 2. So that all cancel out except there'll be a plus 1 and negative 2 to the plus 1 down here. All right, let's write that out. Is going to be the limit as n approaches infinity of the absolute value of, cleaning up my 3 to the n plus 1, 3 to the n will leave me 3 up top. And I'll have an n left over up here. Over negative 2 to the n plus 2, negative 2 to the n plus 1. That'll leave me negative 2 to the 1 down here. So I'll just call it negative 2. All right. Because the n's will cancel out, the 1 will cancel out, leaving us with an extra negative 2 down here. And my n plus 1 will still keep living, n plus 1. All right. Absolute value of that. Okay. So let's see. As n approaches infinity, this will give me the limit as n approaches infinity of the absolute value of 3n over negative 2n minus 2. And as n approaches infinity, these have the same strength. So we'll end up with the absolute value of 3 over negative 2. Because as n grows, negative 2 doesn't matter, 3n and negative 2, and they all win there. And then simplifying the n's, it's that. So we get 3 halves. And what do we know about 3 halves? It is greater than 1. So what do I know? My series diverges by the ratio test. Okay. I really like the ratio test. Yeah, it takes some simplifying down. And if you're having trouble with it, please send me an email or something like that, and I'm happy to talk through and show my whiteboard as I get more comfortable with this tool to help save me time so I don't have to keep running around printing stuff. Sorry, y'all. All right. Here we go. Let's take a look at another example. Let's determine whether this series is convergent or divergent, right? Okay. Same kind of question, but we end up with maybe something a little more interesting here. Yes, that's the reason why I have it as an example. Okay, so this will be, let me go through my process. I need to do the limit as n approaches infinity of the absolute value. Oh, gotta switch over to my pen. Man, oh man. Make sure you do the right thing, Markwalter. All right. So, try that again. We want to find then the limit as n approaches infinity of the absolute value of. I want to do a sub n plus 1. So I want to get here, right? Negative 1 to the n plus 1 over n plus 1 squared plus 1. All right. Yeah, so far that looks pretty good, right? That's all I need. Times, again, I'm dividing by this. So I'm going to multiply by the reciprocal. So I'm going to say n squared plus 1 over negative 1 to the n. I want to see what that gives me. That's going to give me the limit as n approaches infinity of the absolute value of, probably worth cleaning some stuff. I see some negative 1 things will cancel out here. This is going to be kind of interesting to see what goes on down here. So let's see how this looks first. Okay, so for now, I'm going to keep the negative 1 to the n plus 1. I'm going to keep times n squared plus 1. I'm going to keep that there. I'm just keeping everything up top. And that's going to be over n plus 1 squared plus another 1. After I expand this, after I expand that, I'll get n squared. When I FOIL everything out, right? We're not distributing this. We don't distribute powers. We FOIL, so that's n times n. And then n times 1 plus n times 1 gives us plus 2n. Plus 1 times 1 gives us 1 plus 1. That whole thing times the quantity negative 1 to the n. All right. Okay, keep simplifying from there. Maybe we'll start seeing some things happen. This is going to be the limit as n approaches. Ooh, my infinity got real funky. Infinity of negative 1 to the n plus 1 times n squared plus 1 all over. Simplify this whole parentheses thing up here will give me n squared plus 2n. Oh no, I hit a button I don't understand. Abandon ship, Markwalter. It's a close one, y'all. All right. N squared plus 2n plus 2n. Make sure we got their tool back. Plus 2n plus 1 gives me 2n plus 2, right? Times the quantity negative 1 to the n, absolute value of that. Okay, so let's see what cancels out. This is going to be the limit as n approaches infinity of the absolute value of, let's see, negative 1 to the n plus 1, negative 1 to the n. So the negative 1 to the n will cancel out, leaving us with negative 1 to the first power up there. So this will leave me with basically a negative sign, negative n squared plus 1 over, this negative, remember, is really negative 1 to the first power, over the quantity n squared plus 2n plus 2. All right. We're looking at the absolute value of that. Okay. So what goes on as n approaches infinity? Well, n squared and the negative will win up here, so I get negative n squared. The n squared will win down here, so I end up with this. I end up with the limit as n approaches infinity of the absolute value, basically, of negative n squared over n squared, which is the limit as n approaches infinity of negative 1, which is 1. So what does that mean? Well, this is our inconclusive thing for the ratio test. The ratio test is inconclusive at this point. So, am I thinking over here, I'm saying, okay, this is inconclusive. So I got to try a different test. Interesting. I see it's alternating, right? Negative 1 to the n. So if we want to, we can actually go back to our alternating series thing. We say, okay, 1 is the other thing that's not alternating always positive. I can say 1 over n squared plus 1 is always positive. Great. 2. What else do I check for the alternating series? I need to make sure that that it is decreasing eventually. So is 1 over n squared plus 1, is it going to be greater than 1 over n plus 1 squared plus 1 as n grows? And the answer here is yes, because n squared, if I'm taking n, I'm adding a number to it and then squaring it. That's going to make this denominator bigger, which means 1 divided by this thing, a bigger thing, is going to be less than this one. So both of these things check out. My terms that are not alternating, so if I ignore the alternating part, is always going to be positive. As my terms progress, this number is going to be smaller than this number. And I also need to make sure that the limit as n approaches infinity of the terms that are not alternating, n squared plus 1, it should go to 0, and in this case it does. So I can say my series converges by the alternating series test. All right. My ratio test was inconclusive, but my alternating series test did it well for me. You know what's cool about this? It even has like a little stamper thing we could do. We could say all 3 of my alternating series things worked. Hooray! So it does converge, even though my ratio test was inconclusive because the ratio came out to be 1. Okay. So far, so good. Let's keep going. I feel like I'm getting better. All right. Last page here. For what values of x does the series below converge? Now, this is a really important question and one we've not really seen really like this before. We have this series. We want to know what would x need to be so that this thing converges. And this is where the ratio test is really powerful. Let's do the ratio test for this, okay? Let's do the ratio test for this. Switch over to the pen, Markwalter. You got this. Okay. So the limit then, as n approaches infinity, of the absolute value of n plus 1 x to the n plus 1 over 10 to the n plus 1 times, so I did n plus 1s, times the reciprocal of this, 10 to the n over n x to the n. I'm getting a lot better. I think I'm slowly working the system out. I'm proud of myself. You should be proud of me too. All right. So let's see what cancels out. I see some 10 to the n, 10 to the n plus 1. And okay, so let's see how this stuff cancels out. The limit as n approaches infinity of the absolute value of, okay, 10 to the n plus 1, we'll lose the 10 to the n's and leave us with a 10 in the denominator, right? Okay, that's fine. The x to the n, this is x to the n plus 1, we'll lose the x to the n and leave us with an x up top. The n's, unfortunately, here will, in the n plus 1 will just kind of stay. So this is what we'll get, right? Left over in the numerator, we will get n plus 1 times x. This n plus 1 stays, and x to the n plus 1, x to the n, we'll lose the x to the n's, but leave the x to the 1 up here. Over 10 to the n plus 1, we'll lose the 10 to the n's, but 10 to the 1 will still stay down there. 10 to the 1 will stay down there, and we have an n left over that has nothing to cancel out with. All right, so we'll end up with something looking like this. All right, interesting. Well, what happens then as n approaches infinity? Well, as n approaches infinity, we get something like this, right? If I distribute that x, because x is just going to be some number, I want to look for whatever that x needs to be. I end up really with xn plus x over 10n. And typically when I'm doing like my my limits, as n approaches infinity, n's my growing thing. The x to the n is going to win, x times n is going to win, 10 times n is going to win. So I end up with the limit as n approaches infinity of xn over 10n. X is not my growing thing, so it's going to lose the one compared to this. Wait a minute, my n's are going to cancel out. So I end up with this. My limit is the absolute value of x over 10. So what does this mean? I want to know what values of x will make this series converge. I just found out that this ratio test gives me absolute value of x over 10, which I guess I could also write out as the absolute value of x over 10, because 10 is always positive. Now, for the ratio test to tell me something converges, the absolute value of x over 10, the thing that I get has to be less than 1. So what does that mean for me? That means then that the absolute value of x has to be less than 10 if I multiply 10 to this side. This is really important. What this is telling me is if my x value, the absolute value of it, is less than 10, my series will converge. In other words, x has to be between negative 10 and 10. Basically, plus or minus 10 from this moment, from plus or minus 10, right? From 0. The width of this interval, the fact that this interval has a width of 10, the width of the interval over which some series converges is what we call the radius of convergence. And in this case, we found out the radius of convergence. I want to call it radius of convergence in this case. Radius of convergence is 10. But to actually answer this question, what does x need to be? To make it converge, it needs to be that, negative 10 to 10. Interesting, huh? So, I want you to practice the next one that you see below. And then practice the ratio test on the following two. And check your answers and we'll be done. All right. Go ahead, pause the video, practice, and when you get finished, come back. All right. Let's take a look at these last three. All right. So let's go ahead and do our ratio test. We want to know for what values of p does the series converge. It sounds a whole lot like the one before that we just did. This is going to be the limit. That's a rough looking limit. The limit as n approaches infinity of the absolute value of p minus 1 to the 2n plus 1 over 4 to the n plus 1 times, so I did my n plus 1s. Now I'm going to multiply by the reciprocal of this because dividing by this is what the ratio test says, remember. So I'm going to multiply 4 to the n over p minus, just minus, about to do a plus, p minus 1 to the 2n. That's kind of an ugly looking p minus 1, but we got it. All right, so we can clean up some things here. 4 to the n will cancel out, and we'll see what else is left over. So I'm going to do some simplifying of kind of everything here. The limit as n approaches infinity of the absolute value of p minus 1 to the 2n plus, that got a little funky, 2n. When I distribute my 2 up here, I got 2 to the n plus 2, right? 2 to the n plus 2. 4 to the n will cancel out, leaving me with a 4 in the denominator. 4 to the 1 times the quantity p minus 1 to the 2n that's left. Interesting. So I have p minus 1 to the 2n plus 2, p minus 1 to the 2n. So the 2n, p minus 1 to 2n will cancel out, leaving me p minus 1 to the 2 up top. This will be the limit as n approaches infinity of the absolute value of p minus 1 squared, because the 2n's values will get rid of each other, and we'll have p minus 1 to the 2 over 4. Okay, and I want this thing to converge. There are no more n's left. Okay, so what does that mean for me then? All right, so I know then for this thing to converge, I'm going to need the absolute value of p minus 1 squared divided by 4 to be less than 1. But if p minus 1 is squared, the absolute value of that doesn't really matter because something squared is always going to be positive. So what am I really looking at? I'm really looking at p minus 1 squared over 4 needs to be less than 1. So what does that mean? P minus 1 squared has to be less than 4 when I multiply both sides. Okay, interesting. I could either do my, like, think through all of the square roots and stuff here, or I could say this then. I could take the square root, but I got to be careful when taking square roots because I end up with plus or minuses, right? So what do I know now? I could say then, if I take the square root, that uh, -2 is less than p minus 1. Oop, don't need that extra part. Is less than 2. Why? Because I would take the square root here and I'd end up with plus or minus 2, but we're doing with inequalities. So this value here, then whatever p minus 1, it has to be between -2 and 2, because if I squared everything, I'd get 4s back over here. So that's how this taking square root and absolute values works if you've not done that before. And we'll add 1 to both sides, or to all of the sides, not even sides, to everything here. Now I get -1 is less than p is less than 3. All right, so they're the values of p that will make everything work for me. All right, so there's that one. Let's take a look at the practice ones underneath, and we'll be finished. All right, ratio test for convergence. We can do that pretty easily. This is going to be the limit as n approaches infinity. This looks like the ratio test would be useful anyways because I see factorials and powers. That's big giveaway here. We're dealing with k's, but that's fine. We can do 2 to the k plus 1 over k plus 1 factorial times the reciprocal of my original terms, k factorial over 2 to the k. All right. K factorial, k plus 1 factorial, k plus 1 factorial is k plus 1 times k times k. So what is the difference here? Just the k plus 1 will remain underneath because the rest of this will be k factorial, which will cancel out. 2 to the k, 2 to the k plus 1. So I'm going to get the limit as n approaches infinity of the absolute value of 2 to the 1 will be left up top. So that's a 2 over k factorial. K plus 1 factorial shares k plus 1. Nope. K plus 1 factorial is k plus 1 times k factorial. So the k factorial will lose, and we'll be stuck with k plus 1. Sorry, I started over that. Right, 2 to the k, cancel out 2 to the k, leaving us 2 to plus 2 to the 1. K factorial is a lot like this, but this just has an extra k plus 1 multiplied into it. All right, and this is going to be equal to, as n goes to infinity, oh, this shouldn't say n, shouldn't it? These are all k's. I should have said this k from the beginning. I'm sorry. Try to make that look like a k now. Close enough. All right, as k goes to infinity, what happens? Well, k is going to grow down here, so this is going to go to 0, which is less than 1. What does that mean for us? For us, that means that the series converges by the ratio test. All right, and our last one down here, I'm actually going to just rewrite this first because ratio test, it's nice to have fractions because things will cancel out. This is really going to be equal to the series, that should be a k again, huh? K equals 1 to infinity of k over e to the k, right, is really what we're looking at. So let me do my limit. My limit as k approaches infinity of the absolute value of k plus 1 over e to the k plus 1 times the reciprocal of my original series, e to the k, over k, right? This is going to be equal to the limit as k, oh my gosh, I keep messing that up, k approaches infinity of the absolute value of, let's see, k plus 1, those can't cancel out. But e to the k plus 1, some things cancel. This will be k plus 1 over e to the k. We'll cancel out with the e to the k, leaving me with just e times k. As k goes to infinity, we would get the limit as k goes to infinity of the absolute value of k would win up top. ek wins down here as k grows, which leaves me with 1 over, see, k divided by k in terms of strength, 1 over e, which is less than 1. So what do I know? I know that this series also converges by the ratio test. All right. So there's the ratio test, how to use it, and how to use it to determine convergence, the radius of convergence, and what values make something converge. All right. There's a few practice problems to do on the next page, but I want to keep our things relatively short because I really want you to really spend the time watching the video and taking the notes on Taylor polynomials. This is why we're doing what we're doing, really, when it comes down to it. Like, the series stuff, convergence is important, but like, it's all building up to this idea of Taylor polynomials and their usefulness. This video is really, really good. It basically explains everything you need to know conceptually and visualizes it really, really well. Please pay close attention, and then we'll talk about it the next class. Okay? Have a great rest of the day. Be sure to take the check-in quiz and look at my updates as well, particularly about AP exam preparation and interventions, okay? All right. Talk to you later. Bye.